So I'm going to talk about joint work with my collaborator, Paul Hand, who is a mathematician at Northeastern University. And what I'm going to talk about is the deep decoder, which is a way to concisely represent images from untrained neural networks. So there's no training involved. So that's kind of the catch of this talk. All right, so that is an image of the Yosemite National Park, and that's a huge image. So it has 3,000 times 2,000 pixels and so on. So if we were to store each pixel of that image, then we would need to store 4 gigabit of pixels, right? So that's a huge amount. And as we all know, we do not store those pixels. What we do is we store the image in a compressed form. In this particular case, we would store it as a JPEG image, and that is 500 times smaller than if we store it like in a naive way. All right, so like image compression is based on image models, as I assume you know. And the way compression works is in principle very simple. Like given some model for images, we find coefficients such that the image is approximately represented by the coefficients in the model. And here the point is that those coefficients are typically low-dimensional. So they are low-dimensional coefficients that map to a high-dimensional image. And then in order to compress an image, we just fit it, and then we just store the coefficients of that model. And really, anything that we do with images, so may it be image restoration, may it be compression, and whatnot, this typically is always like based one way or the other on image models. So here are some classical image models. So traditionally, all those tasks that I mentioned are based on what I would call like handcrafted image models. And handcrafted image models would be things like wavelets and sparse representations and things like that. So here are some examples. So compression is typically solved with wavelets. For example, JPEG essentially relies on the fact that images can be sparsely represented in wavelets. Denoising is also has been solved using wavelets, and now it's maybe one of the state-of-the-art methods is based on self-similarity. So that is also a handcrafted image model because we assume that the image is self-similar to itself. And then compressive sensing, which is like relevant for like signal recovery from few measurements, that is based on assuming that the image can be sparsely represented in some sort of basis. All right, so those are the traditional ways to represent images. But now all those problems like compression, image restoration, now they are solved using deep neural networks. So for all of the examples I have shown, the state-of-the-art methods are now like deep neural networks, one way or the other. All right, and that has had a huge impact in science and technology. So that's just one example of a company that is based on compressing images in a more concise way using deep nets, right? So that's something I think we are all familiar with. All right, so now typically these deep neural networks, they are trained on large data sets, and there are there are two prevalent ways to train the deep nets. The first one would be using an autoencoder. The second one would be using like a generative adversarial network. And in both cases, what we end up having is we have some sort of generator. And what the generator does is the generator maps some low-dimensional space to some high-dimensional space, right, to the image space. And in both cases, the weights of the network do represent somehow the distribution of the images, and then the input somehow selects from this distribution, right? All right, and kind of to summarize like those facts that I assume to be well known, but I want to make a point here. Here are some facts that I want to summarize. So what we know is that image generating deep networks, they give state-of-the-art performance for all sorts of problems involving images, like compression, denoising, and so on. They are typically trained on large data sets. They are also typically convolutional. They typically have much more parameters than unknowns. And with unknowns, I mean the dimensionality of the image space. Another fact that is kind of agreed on in the community is that there is also something about the network that is particularly useful for representing images. So for example, convolutional networks are particularly useful for representing images. And one paper that made this maybe a little bit more precise is this deep image prior paper. And the deep image prior paper, like I'm quoting it here, it says that a great deal of the image statistics is captured by the structure of a convolutional image generator. And the way how they demonstrated this, or the way how they gave evidence for that, was they took an autoencoder, a convolutional autoencoder, and then they showed that without any training, this autoencoder can be used to solve problems like denoising and image restoration and so on. All right? But this network, just as all the other networks, is also over-parameterized in the sense that it has much more parameters than unknowns. So then the question we were asking in this work was, if neural networks are good at representing images, is there like a version or is there an architecture of deep neural networks that can approximate natural images well using very few parameters and without any training? And here the catch really is this combination of very few parameters and no training, right? And the answer is yes, and that's what I'm going to talk about. So I'm going to talk about an image generating network that has the following properties. It's under-parameterized. It is untrained, so there's no training involved whatsoever. It yields compression and image restoration performance that is like on par with state-of-the-art, but only state-of-the-art of untrained methods. So trained methods still outperform this approach. And it's very simple, and therefore it's useful or interesting maybe for mathematicians because we can prove something about it because it has a very simple structure. All right, so I'm going to call this the deep decoder just to give it a name, so I don't have to say the network, but so let's call it the deep decoder. So it's a non-learned deep image model that has this property that it maps a low-dimensional coefficient space to a high-dimensional image space. And the low-dimensional coefficient space in this case are the weights of the network. So the image is encoded in the weights, it's not encoded in the input to the network. And in order to find the best representation of an image, if we have this model, like all we do is we solve this minimization problem. So we just fit the image to the model, right? And then we have a representation of our image. And before I go into detail how this network looks like, I'm just going to demonstrate that it's, yes? Exactly. The input is going to be fixed, and everything is going to be stored in the weights. Yeah. I'm going to explain the structure in a bit more detail in a second. I'm just going to show one experiment first, just to demonstrate that it actually works in the sense of concisely representing images. So here's the experiment. So what I did is I just took random images from ImageNet, which is, so to say, as taking random images from the internet. It's like cats and dogs and houses and all sorts of things. And then what I did is I represented the image using a certain number of coefficients, and I took like 30 times less coefficients than the output space. So that would be the compression factor, the number of coefficients, the number of pixels over the number of coefficients I used. And then I represented it using this deep decoder, and then I compared to a representation that uses exactly the same number of wavelet coefficients. And the reason why I used wavelet coefficients is that wavelets are known to be good at compressing images. That's why they're used in JPEG. So it's like a solid baseline. And now each point in this plot corresponds to one image. And if we are above the red line, it means the deep decoder representation is better. If we are below the line, it means wavelet representation is better in terms of peak signal to noise ratio. And as you can see here, for a large compression factor, on average, it performs slightly better. And if we have a small compression factor, then wavelets perform slightly better. But it's kind of on par, which is really the point here. So the point is that the deep decoder enables concise image representations. So it's a concise way to represent images. So let's see how the network looks like. So that's how the network looks like. It generates an image from weights using only like those operations. So let me walk you through this in detail. So there's an input to the network, like B1. So that's the input. It's some volume, and we take the volume as fixed. So for example, we can take it random, or we can take it equal to identity. It doesn't really matter. It should just not be degenerate in some sense. So we fix this input once and for all. And then the input is transformed to an image as follows. So first, we take linear combinations of the channels in this network. And that means like we multiply this matrix B with the matrix C. So that's just taking linear combinations. And then multiplying with this matrix U means we are upsampling each channel. And the upsampling is important. So what the upsampling is doing is performing bilinear upsampling. And that turns out to be important. I'm going to comment on it again in a second. And then we apply a ReLU nonlinearity. And then we repeat this a couple of times. So that's all we do. So there's nothing else in this network. And at the very end, we just linearly combine our channels and apply a sigmoid function to it just so it maps to the range 0 and 1, for example. All right, so it's a very simple structure. All it does is upsampling and forming linear combinations, upsampling again and forming linear combinations. So now another way to think about that is that it would be like technically it has no convolutions, right? Because it's just performing linear combinations. But in kind of deep learning world, people would call this 1 times 1 convolutions. So another way to say what's happening here is it's a network that performs 1 times 1 convolutions, and then it upsamples and then performs 1 times 1 convolutions again. So yet another way to think about that would be to say, because upsampling means convolving with a certain kernel. So this can also be viewed as a network that convolves with a fixed kernel and then forms linear combinations, and then it does the same thing again, all right? And that's a crucial point, because the upsampling matters. So that's where kind of a prior assumption about the image is incorporated, like in the upsampling, all right? Okay, so that's a network, right? So that's a network structure. So now maybe one question that I can give some intuition on is like, how can linear upsampling, ReLUs, and linear combinations, how can that synthesize an image efficiently? I'm not going to give a very rigorous argument, just like some intuition, and the intuition is as follows. So let's first recall, what does linear upsampling do? Like here's a vector, right? Like 3-dimensional vector. Linear upsampling would just produce this object. So that's what linear upsampling does. So now how can we represent, like, say, this target image only using linear combinations and upsampling? So we cannot represent this image using only one channel. So we need at least 2 channels for this particular example. So let's start with the first channel. So in the first channel, I chose a vector like this, all right? And then upsampling would produce this particular vector. And then applying the ReLU nonlinearity would give us that vector. All right, and so now let's just put this here and fix it. And now what we need to do next is we need to choose the other channels such that if we add them together or subtract them or something like this, then we get our target image, right? So here's one. So there are many ways to do that. Here's one way. If we choose our signal like this, and then we linearly upsample it, apply the ReLU operation to it, and then we add it to the final signal, then we add it to the other signal, then we get our target signal. All right, so that, I mean, it's a naive example, but it illustrates like 2 things. Like the first thing it illustrates is that, that we can represent like an image with sharp edges by kind of, by upsampling and then linearly combining channels. It also tells us that if we have something that does not have any sharp edges, then we can only upsample it. So in a way, generating something smooth is cheaper than generating something with edges. And therefore, this makes sense as a prior, because if you think about images, images have this property that they are pretty smooth for the most part, but then they have sharp edges. And one kind of big advancement in image processing was this idea of wavelets. And one reason why wavelets are good is because they can represent sharp images as opposed to like Fourier representations, right? So that's also something that can represent sharp edges, but can represent continuous things more efficiently, right? All right. So that's maybe some intuition for why this works. Okay, so it turns out one can show things about it in the sense that, like, with enough parameters, a deep decoder can represent any image. For example, if we have on the order of number of output parameters, many coefficients, then we can represent any image. But the interesting point is that with few parameters, a deep decoder can approximate natural image as well. And then that's something we saw empirically on the first slide. And throughout this talk, and just in general, we work with a deep decoder with very few parameters. All right? So now let's see what else we can do with this deep decoder. So we know already that is a concise way to represent images. So what I want to do next is I would like to make the point that it can be used to solve linear inverse problems, like simple linear inverse problem, and also some like nonlinear inverse problem, like phase retrieval. But I'm going to focus on linear inverse problems. So inverse problems are as follows. We are given some forward model F that maps the image to measurements. And we are then given some noisy measurement, where we apply the forward model to the image plus some noise. And now the goal is, like, given our forward model and given the measurement, we want to reconstruct our image. So how can we solve such a problem with an image model? It's rather simple. When we have a model that maps low-dimensional coefficients to a high-dimensional image, then all we need to do is we can just solve this optimization problem here. So we apply the forward model to the image generated by the model, and then optimize over the coefficients of the model. And in a way, like all the methods to solve linear inverse problem work like this. For example, if you think about like L1 minimization is doing exactly that, but their optimization would be over like some L1 ball, right? So all sorts of things can be mapped into that. And and that's exactly what we do in order to solve linear inverse problems using this image model. So what I want to do next is I want to show how it works on denoising. And the reason why I want to look at denoising is threefold. So why should we care about denoising? Because it's a pretty well-established field. So but it still has practical importance. But maybe more interestingly, like every inverse problem can be solved as a chain of denoising steps, or every linear inverse problem. And therefore, if we can do very well in denoising, then that hints that this method is also going to be useful for inverse problems in general. And it's also an entry point to new mathematical ideas in image processing, so it's a good starting point. So here's the performance of this method for denoising. So what you're seeing here is an image, a noisy image, an image denoised by the deep decoder, an image denoised by the deep image prior. I'm going to talk more about that later, and an image denoised by the BM3D algorithm, which is the best performing algorithm amongst non-trained methods. So what you see from this example is that it is on par with state-of-the-art untrained methods. And I mean, I didn't handpick this image, so like when we performed this experiment where we averaged over a lot of images, and we get the same result. So that's robust. Well, I have to say that like if we have a trained network, right, a trained network outperforms like all these things. Like if the distribution of the training images like is the same as one of the test images at least. Okay, so why does a deep decoder denoise well? The reason is pretty simple. The reason is because it cannot fit noise, and it has too few parameters to fit noise. So here's an example that illustrates this. So if we fit an image, we get an almost perfect representation. That's something we already saw before. If we fit noise, then what we see is we can fit a small proportion of the noise, but not very much, because it has too few parameters to fit much of the noise. And now if we have a noisy image, which would be exactly this image plus exactly this noise, then what happens is it fits the noise, but it doesn't. It fits the image, but it only fits a tiny proportion of the noise. And because of that, it denoises the image. Right? Makes sense? So that's what's going on here. One can also make this precise in the sense of like this theorem. So let's say we take a zero mean variance Gaussian noise vector. So we take this Gaussian noise vector, and let's say it's like n-dimensional. And then what we do is we fit a deep decoder to it. And then what this theorem says is that the fraction of the noise that the deep decoder can represent is lower bounded by, or the fraction that the fraction of the noise that the deep decoder can represent is proportional to log n times m over n. And m over n would be the number of parameters of the network over the number of output pixels. And since the network operates in the underparameterized regime, that tells us that it can only fit a small proportion of the noise, and therefore it denoises. So that would be the argument, and that's the reason why that works. All right, I want to give like a little bit of intuition why that holds, because it's pretty simple and it's close to what we are doing when we do, like, say, sparse recovery. So here's a network with 2 layers. So a network with 2 layers looks as follows. We have this matrix here, like upsampling times the input times the coefficient matrix, and then we apply ReLU to that. And we get a matrix, and then we form linear combination with this vector C dash. And let's call this A just for convenience. So now let's see what the ReLUs are doing. Is the ReLUs are like multiplying this with a diagonal matrix that has either zeros or ones on the diagonal, right? Like depending on whether the corresponding vector is positive or negative. So that's all it does. So therefore, we can write the effect of the ReLU in terms of these matrix multiplications. So each column of this matrix has its own sign pattern, right? And the sign pattern is in this matrix W. And if we do that, then we can represent the output of the deep decoder like shown here, right, as a matrix multiplication. And that is useful because what it tells us is, it tells us that the image of the deep decoder lies in a union of k-square many-dimensional subspaces, right? Because that matrix here would describe a k-square dimensional subspace, and it's a union of subspaces because there are different possibilities for the sign matrices. And now the question is, like, how many different possibilities are there? Like, how large is this union of subspaces? Because that will be important for establishing our denoising rate. So how many subspaces are there? So here's, and the number of subspaces is equal to the number of different sign patterns. And the number of different sign patterns can be bounded using this lemma here. So this lemma tells us essentially, like, if we apply a ReLU in the setup, how many different sign patterns can it generate? And it can generate at most n to the power of square many such sign patterns. All right? And then we have n to the power of k many subspaces. So to summarize, we learned that G of C lies in the union of n to the power of k square many k square dimensional subspaces. And then we can just use this concentration of measure result that tells us that with high probability, at most a fraction of that much of the noise energy lies in one of the subspaces. And if we take a union bound over all those subspaces, then we are still, like, this result still continues to hold with high probability. So that's kind of nice because it's like an analogy to what happens in sparse signal recovery and so on, right? Because there, the argument for denoising would be exactly the same. Like, we would also have this argument, a k-sparse vector lies in a union of subspaces. So it's interesting that the same ideas work here. And that generalizes to some extent to more layers, right? Then the challenge is only how to count the number of sign patterns efficiently. All right, so here's again the denoising performance, and what I compared here to was this work of the deep image prior. And the deep image prior is like a quite interesting work because it's an over-parameterized network. So then the question is, like, how can an over-parameterized network be used to denoise an image? So so it's an over-parameterized network that maps high-dimensional coefficient to some high-dimensional image space. So how can that be used to denoise an image? So here's what happens in the case of the deep image prior. So it's over-parameterized, so it can fit an image essentially perfectly if we train it long enough. If we train it long enough, it can also fit noise perfectly because it's like highly over-parameterized. But what we see here from those two figures is that it takes longer to fit the noise, so it has a harder time of fitting the noise. And therefore, if we have a noisy image, what happens is it first fits the image part, and then it fits the noise part. And if we early stop, if we regularize by early stopping, then what happens is we get kind of like a denoised image. So that's a principle on what this deep image prior work is built. So the deep image prior work is over-parameterized, and therefore it critically relies on regularization. right? Because if we don't early stop, there's no denoising. It's just going to fit to like anything. In contrast, in our work, like our work is under-parameterized, and therefore it doesn't require any further regularization. So that's interesting and useful because it tells us that like all the prior assumptions about the image are in the network. So there's nothing else. Yeah. Yeah, that's a good point. So in that case, if we stop exactly at that point, we kind of get the best performance. But if we just continue, like here we also have the effect, right? Because so here we also have because we have the effect that the deep decoder, it can fit a small proportion of the noise, right? But and now if we also early stop, then we might be even like slightly better. Yeah. Yeah. So we can do that, but it's kind of a tuning parameter, but it doesn't change performance very much. It gives you like half a dB or something. But it's a good point. It's a good observation. Yeah. But it's kind of not crucial for the performance. Yeah. Okay, so I just want to give you like one other example, like an actual real-world example where this works for regularizing like a real-world problem. So in the real-world problem I'm selecting is this compressive sensing, like a classical and well-studied problem where we are given some measurement. So we are given linear measurements of a vector x, or like an image x, right? And A is our measurement matrix. And the goal is, given the measurement matrix A, we want to recover x from y. And for this to be not ill-posed, we need to have some prior assumption or some structural assumption on x, right? And the structural assumption we impose here is that x lies in the range of our image model. As in contrast to like sparse signal recovery, where people assume x is sparse, and that would be the prior assumption or the structural assumption. Okay, and then we can show that this actually does make sense. So let D be a deep decoder, and let Y be some noisy measurement, and let A be a Gaussian measurement matrix. And then the interesting question is like, how many measurements do we need for this to succeed? So what this result says is if M, the number of measurements, is some log factor times the number of parameters of this network, if we take that many measurements, and then we take C hat as a solution to our optimization problem in the compressed domain, so so that's something we can solve based on our few measurements, then with high probability, the error that we make in the image domain is bounded by the representation error that we have. So the representation error would be just the error, like for example, if x star would lie in the range of the generator, then the representation error is 0, plus whatever error we make in terms of the noise, right? So if representation error is 0, and if the noise is 0, then we would get perfect recovery, even if we only have compressive measurements. Okay, but so it sounds kind of it sounds cool, but of course there is an issue with this result, and the issue with this result is like, do we have a solution to this optimization problem? And I mean, here we assume we have the solution, right? But in practice we apply gradient descent. It's highly non-convex. So here the important point is we are making a statement about the solution of the optimization problem, but not about a method to solve the optimization problem, and that's kind of left open for future work. But what I want to demonstrate next is that, like in practice, like gradient descent finds like a really good solution. So this actually like does apply in a way. So here's my example, and since there are so many people from New York University, I took the Facebook New York University fast MRI data set, which is a really interesting data set that was just released like 2 months ago. It consists of lots of case-based measurements from MRI. So what I'm showing here is like full recovery. That would be like an actual image recovered from all the measurements taken from a knee. And what the mask is, the mask corresponds to undersampling by a factor of 8, because that's what we typically do in compressed sensing applied to MRI. And then here, this would be the least squares recovery. It gives us a very blurry image. That would be recovery using L1 minimization and wavelets, and that would be recovery using the deep decoder. And I tried this on like a substantial fraction of the data set, and we consistently see that the deep decoder outperforms L1 minimization. And for this comparison, L1 minimization, or for this setup, L1 minimization is a very fair comparison because it's also an untrained method. So again, if we have a trained method, we might be better. But the point here really is that for, like amongst untrained methods, this works incredibly well, which is kind of interesting. It really tells us that like deep networks, even if we use them in an untrained way, they function as like a really good image model. So there are a lot of assumptions that are already like baked in our network. So that's kind of the gist of my talk. So to summarize, the deep decoder is a simple deep neural network image model. It's untrained. It enables concise image representations. It comes with some mathematical guarantees, and hopefully in the future we're going to establish more, and it gives us performance that is on par with state-of-the-art for linear inverse problems based on comparison to non-trained method, right? And yeah, so the code is available if you like to reproduce those results, and yeah, that's our paper that will be in ICLR.